Your API gets 50,000 requests in 1 minute. From one user, your server chokes, every other user gets a 503. Your database runs out of connections. Your cloud bill doubles overnight, and the attacker paid nothing to do it. Rate limiting is the mechanism that prevents exactly this. It is one of the most overlooked things developers skip when building their first API, and one of the most expensive lessons to learn in production. In this video, we are going to break down what rate limiting actually is, how the algorithms work, what attacks it stops, and how to implement it the right way. Without rate limiting, your API is completely open. One user, one bot, or one accidental infinite loop can consume all your server resources. There is no ceiling on how many requests any single client can send. The consequences are predictable. Your server runs out of memory and crashes. Your database exhausts its connection pool and queries timeout. Your cloud bill spikes because you are paying for every compute cycle, even the ones used to attack you. The worst part is that your legitimate users suffer the most. They send a request, they get nothing back, and they do not know why. Rate limiting puts a ceiling on how many requests a client can make in a given time window. It is the difference between an API that can be abused and one that cannot. Rate limiting controls how many requests a client can make in a fixed time window. That is the definition. A client tries to make a request. Rate limiter checks how many requests that client has already made in the current window. If they are under the limit, the request goes through. If they are over the limit, the request is rejected immediately with an HTTP 429 status code, which means too many requests. The response includes a retry after header telling the client how long to wait before trying again. Rate limiting is not a firewall. It does not protect against SQL injection or authentication attacks. It is not a substitute for proper auth, and it is not the same thing as throttling, although the two terms are often used interchangeably. Throttling slows requests down, rate limiting blocks them entirely. The most commonly used rate limiting algorithm is the token bucket. Imagine a bucket with a maximum capacity of, say, 100 tokens. Tokens are added to the bucket at a fixed rate 1 per second. Every incoming request costs 1 token. If the bucket has tokens available, the request goes through and 1 token is removed. If the bucket is empty, the request is rejected. The bucket allows short bursts up to the bucket capacity, but enforces a sustained rate equal to the refill rate over time. This is ideal for most APIs because it tolerates legitimate spikes while preventing sustained abuse. Other algorithms exist. The fixed window counter is the simplest, but it suffers from boundary bursts where a client can double the allowed rate by hitting requests at the end of one window and the start of the next. The sliding window log is the most accurate but uses the most memory. The leaky bucket produces smooth output at a fixed rate with no bursts allowed at all. Rate limiting directly neutralizes several of the most common API attacks. Credential stuffing is when a bot tries thousands of username and password combinations against your login endpoint. Without rate limiting, one IP can attempt 10,000 logins per minute. With a limit of 5 attempts per minute per IP, that attack becomes economically unviable. Data harvesting is when a competitor loops through your search or product API to scrape your entire catalog. Rate limit to 1 request per second per API key, and the scraper would take years to finish. Resource exhaustion is when an expensive endpoint like a report generator that runs a heavy database query gets called in a loop. 5 requests per minute on heavy endpoints puts a hard ceiling on how much compute any one client can trigger. None of these require sophisticated detection. The rate limiter just counts. When you reject a request with a 429 status code, you must return the right headers so clients can recover gracefully. Retry after tells the client the number of seconds until they can try again. X-rate limit tells them how many requests are allowed in the window. X-rate limit remaining shows how many requests they have left in the current window. X-rate limit reset is the Unix timestamp when the window resets. Good API clients read these headers and back off automatically. Bad clients ignore them, but returning them is your obligation as an API designer. A well-formed 429 response with a JSON body explaining the error and a retry after header is what separates a professional API from one that just silently drops requests. There are 4 main strategies for choosing what dimension to rate limit on. Per-IP limiting counts requests by source IP address. It is easy to implement, but bots can distribute across many IP addresses to evade it. Per-user limiting counts by authenticated user ID. This is fairer because power users can be given higher quotas than anonymous users. Per-API key limiting is the standard approach for developer-facing APIs and SaaS products. Free tier keys get 100 requests per minute. Paid keys get 1,000. It is also your monetization lever. Per-endpoint limiting applies different limits to different routes. Your lightweight get endpoint might allow 1,000 requests per minute. Your CPU-intensive report endpoint might allow 5. In practice, most production APIs layer these strategies together. Per-IP blocks distributed bots. Per-user protects your paying customers. Per-endpoint protects your expensive operations. In your stack, rate limiting can live in multiple places. At the CDN or edge layer, providers like Cloudflare and Fastly can apply coarse IP-based throttling before traffic even reaches your servers. This is your first line of defense. At the API gateway layer, tools like Kong or AWS API Gateway let you configure per key and per route limits as policy, not code. At the application layer, your Express or Fast API service can enforce business logic rules like different limits for different user tiers. The rate limit state itself lives in a fast data store, almost always Redis. The implementation is just a counter. You increment a key that represents the client and the current time window. You set a TTL equal to the window duration. If the counter exceeds the limit, you reject the request. This is atomic, fast, and works across multiple application instances. Here is your implementation checklist. Choose the token bucket algorithm unless you have a specific reason not to. Pick your limiting dimension, starting with per API key for developer APIs and per user for authenticated consumer apps. Set a sensible default. 100 requests per minute is a reasonable starting point for most endpoints. Always return a 429 with a retry after header, never just drop the request silently. Use Redis for your counter store if you run more than one instance. Give trusted and paid users higher quotas. Monitor your rate limit hit rate. If 10% of your traffic is hitting the limit, your limits are probably too tight. And test before you ship. A rate limiter that is too aggressive will frustrate your real users more than it deters attackers. Rate limit early, monitor constantly, and tune based on what you see in production. Rate limiting is one of those things that feels optional right up until the moment you need it. And at that moment, you really need it. The good news is that it is not hard to implement. A Redis counter and a middleware function is all it takes to protect your API from the most common abuse patterns. If you found this useful, subscribe for more systems concepts explained visually. Thanks for watching.